Assalamu alaikum. Welcome to part 2 of our lecture on the last part of chapter 7. So, kalamna on Modua, conservation of energy. And we expressed it in this way, that the change in the kinetic energy plus the change in the potential energy plus the change in the internal energy, which is determined by the work done by the non-conservative forces, is equal 0. This is a principle we can use in any case where we have both conservative forces and non-conservative forces. And then we looked at an example. So you will remember we talked about your little brother with a skateboard, and he skated to the bottom of the ramp, and we used conservation of energy to calculate his speed at the bottom of the ramp. So the potential energy, gravitational potential energy, changed to kinetic energy. So there was a reduction in gravitational potential energy equal to mgh, and the change in and that potential energy became kinetic energy. So in fact, what we found was that the velocity was the same as if it would be in free fall, because all of the work was done by gravity, even though now his velocity is in a different direction than it would have been if he had been in free fall. It's in the horizontal direction. That is the effect of the normal force. But the normal force did no work, although it changed the direction of the velocity. And then the second part of the question was the normal force at the bottom of the ramp. And in that case, we used Newton's laws. And we showed that the normal force was equal to 882 newtons. So it's 3 times the boy's weight, because he's going in circular motion, and so he's accelerating upwards, and he is putting extra force onto the ground, and so the ground has a reaction force which is greater than his weight. So now I want to look at another example of the use of the conservation of energy. So this is going to be a case in which, again, we're going to have both conservative and non-conservative forces. Okay, so in this case, we're going to have a block. الماس بينزل من فوق. It's 200 kilograms. And it's moving downwards with a velocity of 4 meters per second. We'll call that V naught. And then it hits a platform which is connected to a spring. And when it hits the spring, then the spring compresses. The spring compresses by 2 meters. So we'll call that distance h. And then after it's compressed by 2 meters, the velocity is 0. the mass comes to a stop. Now, during this time, friction was in the spring and exerted a force 17,000 newtons. واتجاه friction عكس من الحركة، لذلك الفريكشن اتجاهها فوق. Okay, so now we have the mass, we have the initial velocity, we have the height, and we have the force due to friction. And now the question I want to ask is, what is the spring constant? So I'll give you a few seconds to think about that and pause the video if you want to actually work it through before we continue. Okay, so because we're talking about conservation of energy, we can guess that we should be able to use conservation of energy to solve this problem. So because we have conservative and non-conservative forces in the problem, we need to use conservation of energy in the following form. So you remember we have the initial kinetic energy plus the initial potential energy plus the work done by the non-conservative force, which here is friction. Must be equal to the final kinetic energy plus the final potential energy. Okay, so do we have what we need to calculate all of these things and just leave the spring constant? Well, let's see. Now, خلي بالك عشان هنا في 2 potential energy عشان في 2 قوة محافظة. Gravity, well, spring. Okay, so the initial kinetic energy should be 1/2 m v naught squared. And then we have the initial gravitational potential energy. Now فاكر لازم نختار الcoordinate system. وهنا أعتقد أحسن اختيار الزيرو الموقف الآخر. ماشي? So we'll make the 0 point at the lowest point here. Then in that case, the initial potential energy at this point is mgh. Then we have the spring potential energy. The initial spring potential energy, initially the spring is not compressed, so that's 0. Then we have the work done by friction. What's the work done by friction? The work done by friction should be, in this case, the friction is moving in the direction, the friction is pushing in the direction opposite of the displacement. So there's a 180-degree angle between the direction of the friction and the direction of the displacement. And cosine of 180 degrees is -1. So عندنا minus 17,000 newtons times h. So let's call this, let's stick with the symbols now. So we'll call it minus F times h. And then we have the final potential energy. Sorry, we equate that to the final kinetic energy, and the final kinetic energy is 0. because the mass comes to rest. And then we have the final potential energy. The final potential energy from the gravity is equal to 0. And the final potential energy from the spring is equal to 1/2 k h squared. So نعرف M، نعرف V naught و H و F. So everything is known except K. So we can directly solve for K. K, Sawi. We're going to have now all of this. So 1/2 mv naught squared plus mgh. And then we have minus fh. And then we need to divide that by 1/2 times h squared. Okay. And this, we usually use a small k. So all we have to do is substitute in those numbers. So we have, we can cross out, of course, the 1/2. Okay, and if we substitute all those numbers in, we get mv naught squared will be 200 kilograms times 4 meters per second squared. And then we'll have 200 kilograms times 9.8 meters per second squared times 2 meters. And then we have minus 34,000 Newton meters, or minus 34,000 joules, and we'll divide that by 4 meters squared. So I'll let you substitute in the numbers, but I will do one thing here. I'll just check the units. So here we have mass, which is kilograms. Then we have meters squared per second squared. So that's kilograms meters per second squared, which is a Newton, and then another meter. So it's a Newton meter, which is a joule. And here we have kilograms, and then we have meters per second squared. Kilogram meters per second squared is a Newton. And then from H we get meters. That's Newton meters, which is a joule. And here we have newtons times meters. So it's Newton meters, which is a joule. So on top we have kilograms meters squared per second squared. And on the bottom we have meters squared. So let's just go through that. Kilograms meters squared per second squared and then we divide that by meters squared. So that gives us kilograms per second squared. صح ولا غلط? Is that what we should be getting? Well, remember that K is defined by F is the spring force equal to minus K times X. So K would be F over X, and F is newtons, which is kilograms meters per second squared, and then we divide by x, which is in meters. That gives us kilograms per second squared. So alhamdulillah, we had the correct units. Okay, so now before we talk about the relationship between force and potential energy, I want to just mention one other topic, which is the power. So power موضوع بسيط جدا. Definition is the work per unit time. Or we could say the rate at which work is done. So we would define it mathematically using the calculus. We would have P equal to the limit as delta T goes to 0. Of delta W over delta T. Okay, so now let's assume we can write then the delta W. So we could write delta W is equal to F, the parallel component of F, times delta S. So this is delta W equal F parallel times delta S. And so we can rewrite that readily. So we can say that delta W over delta T, which is what we're going to need in the limit, is equal to F parallel times delta S divided by delta T. But delta S over delta T is just the speed or the magnitude of the velocity. So if we took the parallel component of the force and we multiply it by the magnitude of the velocity, this is just equal to, as we go into the limit as delta T goes to 0, this is just force scalar product with V. Remembering that V is in magnitude equal to delta S over delta T. In the limit as delta T goes to 0. تمام? Okay, so the power is very easy to calculate. Sometimes you will be given the amount of work and the amount of time, and you would be asked for the average power. then the average power would simply be total work over total time. But if you need the instantaneous power, then if you have the force and the velocity, you can calculate it in this way. Okay, so now I'm going to go back to the theme we mentioned at the beginning, which is a very important theme in physics, which is the relationship between the work and the potential energy. Or more specifically, what we call the potential gradient. Now, let's go back and consider the definition we had of the change in potential energy. So remember, we said that the change in potential energy is equal to minus the work done by the force and this in turn we can write as minus force dot product with a displacement and we could rewrite this then in the case where we're looking at infinitesimally small change, infinitesimally small movement, then we would say that the associated potential energy is equal to minus, let me just make it clear here, these are vectors. So for the infinitesimally small displacement, we take the instantaneous value of the force and we take the dot product with the infinitesimally small displacement. And now I can rewrite this equation in one dimension. So if I have the case of one dimension, then I can use a little trick here. And I can say that I can divide both sides of the equation by ds, because now we don't have any cosine here. So we will have du ds, or since it's one dimension, we could write this, let's say, as dx, and this will be equal to minus f. Or f equal minus du dx. Now I should make this f the f in the x direction, because I assumed that this motion was in one dimension. So it should be in the same direction as the displacement, x. Okay, so you see, if we have the potential energy and we have it as a function of x, we can take this derivative if it's a continuous function of x, and we have the component of the force in the x direction. So دي فكرة جميلة في فيزياء عشان as you see, as you're going to be studying physics in the future. So for example, when you go to 102, physics 102, and more advanced courses or engineering courses or biology or chemistry courses, then the potential energy is going to be what tells you about the system. Because if you solve for the potential energy, then you could readily generate the force, and then you can predict all the motion in the system. So the potential energy, هو مفتاح classical mechanics, actually, even though you can't see it. Even though you can't see it, but we used our imagination, we used mathematics, and we showed that there's something there, because all of the predictions that we make from this potential energy describe what happens in the real world. Now, this was in one dimension. Now, I'm not going to prove this to you in 3 dimensions, but I think we can imagine from what we've seen now that this would be the case, that in 3 dimensions, we can say that the infinitesimal change in potential energy would be minus the x component of the force. So actually, this is going to be a dot product between F dot S minus F dot S. This is the total change in the infinitesimal movement. This will be F dot ds. Okay, so then we can write that out. We can write out that that dot product in the following way. We have minus f sub x dx and then we have minus f sub y dy, and then we have minus f sub z times dz. So now each of these components of f, we can write in the way that we wrote the x components. So f sub y will be equal to minus du dy, and f sub z will be equal to minus minus du dz. But now, formally, in math and calculus, we shouldn't really write this as a derivative like this. This is a different kind of derivative. This is called partial derivative. And we really, in truth, we write it like this. So f sub x should be equal to what we call the partial derivative of u with respect to x. So we write it. We write the partial derivative with a special symbol like this. So this is partial u with respect to x, And let's not forget that we need to have a negative sign in front. Okay, I'm just putting the negative sign. Okay, so we have partial of u with respect to x. And we would have the same thing for fy and fz, but instead we need to take minus the partial derivative of u with respect to y, and so forth. So you can extrapolate what it would be for z. Now, with this partial derivative, we need to formally say something else. We are taking the derivative while we're taking the derivative with respect to x while we hold y and z constant. Here, we're taking the derivative with respect to y while we hold x and z constant. And for f of z, we will take the partial derivative minus the partial derivative with respect to z while we hold x and y constant. Okay, so this is the formal definition. And so we can actually derive a vector force from the potential energy, which was a scalar. So sometimes we write this a little bit different. So we would say something like F is equal to what's called the gradient of u. So the gradient converts a scalar to a vector. So it's like this. Partial with respect to x times I hat plus j hat times partial with respect to y plus k hat times partial with respect to z. Now these partial derivatives ده فكرة جديدة يمكن غريب شوية. Let's look at it بالصورة. Let's say we have مثلا potential energy which is a function of x and y. belash z in this example. Okay, so now let's plot that against x and y. So here's x axis, here's the y axis. And then we will have u in the vertical axis. وهنا في surface. So this is x and this is y. هنا في surface. So for any given value of x and y في رقم u. وكل الأرقام u على السبيس d بيعمل a surface. So now imagine on this surface I just take cuts through مثلا at different positions in y. So here I have y يساوي y0, y يساوي y1, y يساوي y2. وعلى الخط هنا on this line y يساوي constant. Y doesn't change on that line. عندنا a curve هو u of x and y versus x. يعني زي كده. So it's like this. So this is u of x, which is a variable x, and y naught, which is constant over this interval. So its shape is something like this, as I drew it there. Okay, so now partial of u with respect to x, y naught, partial of u with respect to x. Remember, we write it with this little y equal y naught. This is the slope of this curve. So in other words, we take a cut through the surface to make a line. We slice it. We slice it at a constant value of y. And then we take the slope of the line that intersects with that slice, and that slope is partial of u with respect to x. And the other way around. If I take a slice here at a constant value of x, then the slope of u along that line will be the partial of u with respect to x. So notice this partial derivative will have a different value depending on the constant value for y and z. Okay, so now let's look back. Actually, I forgot the negative sign here. The force is equal to minus the gradient times u, or the components of the force are equal to f of x minus du dx, f of y minus du dy. So the force will always be in a direction which will cause the potential energy to decrease. So now let's look here. Let's look at this slope. Partial of u with respect to x, that is minus the force. Tamam? Okay, so if partial u with respect to x is positive, then the force is negative. وَالْعَكْس. Okay? So, مثلا, هنا الgradient هو positive. لذلك القوة هو negative. So the direction of the force we can see directly from the diagram. The force is in the opposite direction from the gradient of the potential energy along this dimension. This is, I should say, this is the direction of f of x. It doesn't tell us the direction of f of y. To find the direction of f of y, we need to take a slice, a fixed value of x, yani parallel to the y-axis, and then take its slope. So what does this mean? This means ala surface هنا, ala surface potential energy surface, دائما القوة في اتجاه عكس من السلوب. عشان كده القوة هو هيعمل حركة ولا acceleration في تحت. Yani the forces now will act on the object to tend to make them go down on the potential surface. So the further down I go in the potential, the more I am responding to the force. So let's just look at that. Belsura. We'll look at it in one dimension. So as we said, the force in the x direction is equal to minus the derivative of u with respect to x. So in regions where u changes the most rapidly with x, this corresponds to a large force magnitude. Also, when f of x is positive, is in the positive x direction, u of x must be decreasing with increasing x. And a conservative force always acts to push the system toward lower potential energy. So, مثلا, in the case of gravitational potential energy, here's the gravitational potential energy, plotted as a function of y. So you see that as y decreases, the potential energy decreases. Okay? So as y increases, the potential energy increases. عشان كده السلوب هو positive والقوة negative. So we have a negative force as a function of y. And it's constant. It's constant. It's just equal to minus mg. And that force will tend to pull us down, as gravity tends to pull us down. And in 3 dimensions, then as you see, we write the components of the force, the individual components of the force, using the negative of the partial derivative of the potential energy function. And so this is actually a vector equation. So here is the gradient operator. The gradient operator, تغير السكيلر إلى الفector. the scalar potential energy is changed into the vector force. So هنا في صورة في one dimension potential energy بالموقف، وفي أي نقطة الكاوة يساوي الgradient الslope. مثلا هنا the slope is negative. In these first 2 points, the slope is negative. عشان كده the force is positive. The force is positive, it pushes towards positive x. So the object goes down the hill towards positive x. When it reaches this point, عند النقطة دي اتجاه potential energy غير. So the potential energy begins to increase. Now the slope is positive. عشان الslope يعني partial of u with respect to x هو positive, الكاوة negative في اتجاه negative x. And this will push the object back to this point. So the lowest point, if the object is at the lowest point ومن غير طاقة حركية هو مبسوط عشان ما فيش force. The slope of u versus x here is 0. عشان كده الكاوة يساوي 0. And we call this stable equilibrium. وشوف يمكن بنفس potential energy في أكثر من واحد نقطة equilibrium. مثلا هنا the force is 0 because the direction of u is changing. Okay, so before this point, there is a negative slope to the potential producing a force in the positive direction. Then once we pass this point, there's a force pushing it back. So this is a stable equilibrium. Now notice في نقطة تانية مع slope 0 مثلا هنا وهنا، ولكن يختلف من نقطة هنا. الاثنين هم نقطة equilibrium. Wherever we have a force equal to 0, we have an equilibrium, at least in this dimension. And that means that if the object sits in the equilibrium point and it has no velocity, it will هو مبسوط. يعني كده. ولكن النقطة equilibrium فوق يختلف من نقطة equilibrium تحت. عشان عند نقطة equilibrium تحت لو في أي حركة من نقطة الكاوة في اتجاه العكس. So the force pulls the object back to the equilibrium point. ولكن هنا العكس فوق العكس. لو في أي حركة من نقطة equilibrium الكاوة هيعمل كاوة في اتجاه برا. So the force when you deviate from this equilibrium point will always push you away from the equilibrium. So اسمه النقطة على النقطة من تحت مع slope 0 اسمه equilibrium، ونفس اسمه النقطة فوق equilibrium، ولكن تحت في stable equilibrium، فوق في unstable equilibrium. Okay, so that is it for our formal lectures. And this really is the material that you're responsible for on the final exam up to what we've presented here, and of course the examples in the homework and in the pre-lecture quiz and the clinic, which are all covering these concepts. So all of it should be related to the concepts that we covered here. So we talked about the work kinetic energy theorem. We talked about the potential energy. We talked about how to calculate the force and the work done when the forces are not constant. We talked about the conservation of mechanical energy in the presence of conservative forces, and how we need to change the equations when we have non-conservative forces. We looked at those examples where we had friction as a non-conservative force, and we looked at a few examples of how to solve problems using the conservation of energy. أحيانا أسهل من قانون نيوتن. Sometimes it's easier than the second law. And if you look in the problem-solving strategies in the book, you'll see they give you some tips of how to decide when to use Newton's laws or when to use conservation of energy. But notice we derived everything we said about conservation of energy and the potential energy from Newton's laws. يعني حقيقة مش حاجة جديدة. We derived it all from Newton's laws, but once we derived it, it gives us some shortcuts in some problems to solve some of those problems. And as we said, there are different ways that you can describe physics. So for example, you can start with Newton's laws and derive the potential energy, but you can also start with the potential energy and derive Newton's laws. And that's what we showed now. We do it using the gradient. Okay, so we will have our last sessions next week, and then you can ask questions about some of these this last lecture, and then we will give you a voluntary quiz for bonus points during the period between the end of let's say, we'll give it to you next week, early next week. That is early the week of the 3rd of January. And then we'll have to decide, I'm not sure exactly what the policy is going to be on when it should be due, given now we have the delay before the final exams. But you will have a certain amount of time to do those bonus points. I think probably we have to do it in time to give you the grades. So it will probably have to be due the end of the week of the 3rd, so that we can add the points to your grades. And good luck. Good luck on the exam and on the makeup exams for those of you who need to take it. And we will see you in the question and answer sessions and the office hours. Assalamu alaikum.